Hello students, let's discuss about t-test. The t-test is the most commonly used method to evaluate the differences in means between two groups. Theoretically, the t-test can be used even if the sample sizes are very small as 10, as long as the variables are normally distributed within each group and the variation of scores in two groups is not reliably different. Let's look into the details. Statistical analysis of t-test, independent one sample t-test, independent two sample t-test, dependent t-test for paired samples. The t-test was described by William Seeley Gossett for monitoring the brewing at Guinness in Dublin. Guinness considered the use of statistics is trade secret, so he published his test under the pen name Student. Hence, the test is now often called the student's t-test. The t-test gives an indication of the separateness of two sets of measurements and is thus used to check whether two sets of measures are essentially different. The typical way of doing this is with the null hypothesis that means of the two sets of measures are equal. The t-test assumes a normal distribution, that is a parametric data, and the underlying variances are equal. It is used when there is random assignment and only two sets of measurement to compare. There are two main types of t-test. Independent measures t-test when samples are not matched, and matched paired t-test when samples appear in pairs, that is before and after test. A single sample t-test compares a sample against a known figure. For example, where measures of a manufactured item are compared against the required standard. The t-test assesses whether the means of two groups are statistically different from each other. This analysis is appropriate whenever you want to compare the means of two groups, and especially appropriate as the analysis for the post-test only two group randomized experimental design. The figure 1 shows the distributions for the treated, that is blue, and control group, that is green groups in a study. Actually, the figure shows the idealized distribution. The actual distribution would usually be depicted with a histogram or bar graph. The figure indicates where the control and treatment group means are located. The question the t-test addresses is whether the means are statistically different. What does it mean to say that the averages for two groups are statistically different? Consider the three situations shown in figure 2. The first thing to notice about the three situations is that the difference between the means is the same in all three. But you should also notice that the three situations don't look the same. They tell very different stories. The top example shows a case with moderate variability of scores within each group. The second situation shows the high variability case. The third shows the case with low variability. Clearly, we would conclude that the two groups appear most different or distinct in the bottom or low variability case. Why? Because there is relatively little overlap between the two bell-shaped curves. In the high variability case, the group difference appears least striking because the two bell-shaped distributions overlap so much. This leads us to a very important conclusion. When we are looking at the differences between scores for two groups, we have to judge the difference between their means relative to the spread or variability of their scores. The t-test does just this. Statistical analysis of the t-test. The formula for the t-test is a ratio. The top part of the ratio is just the difference between the two means or averages. The bottom part is a measure of the variability or dispersion of the scores. This formula is essentially another example of signal to noise metaphor in research. The difference between the means is a signal that in this case we think of our program or treatment introduced into the data. The bottom part of the formula is a measure of variability that is essentially noise that may make it harder to see the group difference. Figure 3 shows the formula for the t-test and how the numerator and denominator are related to the distributions. That is, the difference between group means divided by variability of groups, that is t, that is mean of t minus mean of c divided by standard error of mean of t minus mean of c. The top part of the formula is easy to compute. Just find the difference between the means. The bottom part is called the standard error of difference. To compute it, we take the variance for each group and divide it by the number of people in that group. We add these two values and then take their square root. The specific formula is given below, that is standard error t is equal to mean of t minus mean of c divided by the square root of variance of t divided by n of t plus variance of c divided by n of c. The t value will be positive if the first mean is larger than the second and negative if it is smaller. Once you compute the t value, you have to look it up in a table of significance to test whether the ratio is large enough to say that the difference between the groups is not likely to have been a chance finding. To test the significance, you need to set a risk level called the alpha level. In most social research, the rule of the thumb is to set the alpha level at 0.05% level. This means that 5 times out of 100 you would find a statistically significant difference between the means even if there was none. Degrees of freedom. You also need to determine the degrees of freedom for the test. In the t-test, the degrees of freedom is the sum of the persons in both groups minus 2. Given the alpha level, the degree of freedom and the t value, you can look the t value up in a standard table of significance. It is available as an appendix in the back of most statistics texts. To determine whether the t value is large enough to be significant. If it is, you can conclude that the difference between the means of two groups is different. Fortunately, statistical computer programs routinely print the significance test results and save you the trouble of looking them up in a table. Calculations. Explicit expressions that can be used to carry out various t-tests are given below. In each case, the formula for a test statistic that either exactly follows or closely approximates a t distribution under the null hypothesis is given. Also, the appropriate degrees of freedom are given in each case. Each of these statistics can be used to carry out either a one-tailed or a two-tailed test. Once a t value is determined, a p value can be found using a table of values from students' t distribution. If the calculated p value is below the threshold chosen for statistical significance, usually at 10% level, 5% level and 1% level, then the null hypothesis is rejected in favor of alternate hypothesis. Independent one sample t-test. In testing the null hypothesis that the population mean is equal to a specified value mu0, one uses the statistic t is equal to x bar minus mu0 divided by s divided by root of n, where s is the sample standard deviation of the sample and n is the sample size. The degrees of freedom used in this test is n minus 1. Independent two sample t-test, where there is equal sample size and equal variance. This test is only used when both, that is the two sample sizes, that is the number of participants in each group, are equal. It can be assumed that the two distributions have the same variance. Violation of these assumptions are discussed below. The t-statistic to test whether the means are different can be calculated as follows. T is equal to x1 bar minus x2 bar divided by S x1 is x2 into root of 2 divided by n, where S x1 x2 is equal to root of 1 by 2 into S x1 squared plus S x2 squared. Here S x1 x2 is the grand standard deviation or pool standard deviation. 1 is equal to group 1 and 2 is equal to group 2. The denominator of T is the standard error of the difference between two means. For significance testing, the degrees of freedom for this test is 2n minus 2, where n is the number of participants in each group. Unequal sample size, equal variance. This test is used only when it can be assumed that the two distributions have the same variance. The t-statistics to test whether the means are different can be calculated as follows. T is equal to x1 bar minus x2 bar divided by S x1 x2 into root of 1 by n1 plus 1 by n2, where x1 x2 is equal to root of n1 minus 1 into S x1 squared plus n2 minus 1 into S x2 squared divided by n1 plus n2 minus 2. Note that the formula above are generalizations of the case where both samples have equal sizes. S x1 x2 is an estimator, the common standard deviation of the two samples. It is defined in this way so that its square is an unbiased estimator, the common variance, whether or not the population means are the same. In these formulae, n is equal to number of participants, 1 is group 1, 2 group 2, and n minus 1 is the number of degrees of freedom for either group, and the two sample size and the total sample size minus 2, that is n1 plus n2 minus 2 is the total number of degrees of freedom which is used for significance testing. Unequal sample sizes, unequal variance. This test is used only when the two population variances are assumed to be different and hence must be estimated separately. The t-test to test whether the population means are different can be calculated as follows. T is equal to x1 bar minus x2 bar divided by S x1 bar minus x2 bar, where S into x1 bar minus x2 bar is equal to root of S1 squared divided by n1 plus S2 squared divided by n2, where S squared is the unbiased estimator of the variance of the two samples. N is the number of participants, 1 group 1, 2 group 2. Note that in this case S x1 bar minus x2 bar is not a pooled variance. For use in significance testing, the distribution of the test statistics is approximated as being an ordinary student's t distribution with the degrees of freedom calculated using degree of freedom is equal to S1 squared divided by n1 plus S2 squared divided by n2 the whole squared divided by S1 squared divided by n1 the whole squared divided by n1 minus 1 plus S2 squared divided by n2 the whole squared divided by n2 minus 1. This is called the Welch-Satterthwaite equation. Note that the true distribution of the test statistic actually depends on the two unknown variances. Dependent t-test for paired samples. This test is used when the samples are dependent, that is, when there is only one sample that has been tested twice, or when there are two samples that have been matched or paired. This is an example of paired difference test. T is equal to xd bar minus mu 0 divided by sd divided by root of n. For this equation, the difference between all pairs must be calculated. The pairs are either 1% pre-test and post-test scores, or between pairs of persons matched into meaningful groups. The average and standard deviation of those differences are used in the equation. The constant mu 0 is non-zero if you want to test whether the average of the difference is significantly different from mu 0. The degree of freedom used is n minus 1. Interpretation. The resultant t value is then looked up in a t table to determine the probability that a significant difference between the two sets of measures exists, and hence what can be claimed about the efficacy of the experimental treatment. Discussion. The t-test is a basic test that is limited to two groups. For multiple groups, you would have to compare each pair of groups. For example, with 3 groups, there would be 3 tests, AB, AC, BC. While with 7 groups, there would be 21 tests. The basic principle is to test the null hypothesis that the means of 2 groups are equal. A significant problem with this is that we typically accept significance with each t-test of 95%. For multiple tests, these accumulate and hence reduce the validity of the results. Advantages and disadvantages of t-test. T-test advantages are that they work well with 2 means, so they are good for ratio data and such. It shows whether they have significant differences. However, if 2 means are large, it will give a significant value.